Assuming you got to the point that double slits were understandable and doable, there's not a big jump to go from a double slit to a grating. There's really just one extra step. A grating is a bunch of lines scratched into a particular distance. That tells you the D value. The D value isn't given directly as it used to be for double slits. So the D value in this case, it's got 500 lines in 1 centimeter. So the D value is going to be 1 centimeter, or if I put that into meters, divided by 500. Do the math on that, crunch it out. That's a funny number, 2 times 10 to the negative 5 in meters. That's the D value of this particular grating. Then the rest of it falls apart just like a double slit question would. The lambda, we'll convert that to meters. 630 nanometers is 6.3 times 10 to the negative 7 meters. The screen is 2 meters away. If it says the distance between consecutive bright spots, the bright spots, usually for a grating, we'll talk about the bright spots since they're so localized, since they're so narrow. So the pattern for a diffraction grating would be just these stripes of lines, these stripes of where the light is showing up. If we know the distance between consecutive bright spots, just like we did with the double slits, that's the n equals 1 condition. So for this one, since I want to know the distance between consecutive bright, I want to know what y corresponds to n equals 1. Our condition for gratings is the same as for a double slit. dy over L equals n lambda. Now it's just a matter of grinding out and finding the y. The d after our division was the 2 times 10 to the negative 5 number. I don't know why. The L was given as 2. Since we're bright to bright, the n equals 1, and the lambda, nice shade of red, 6.3 times 10 to the negative 7. Doing the math on that, I get y equals 0.063 in meters, or if you wanted to, 6.3 centimeters. That is how we're going to tackle a grating question. It's really just that extra